Hi, I'm Hannes, and today we have Chaitanya presenting his blog post, another paper today, on recent advances in DL for combinatorial optimization problems. And if you want to join these reading group sessions yourself, you can find all of the information in the description. All right, but then, Chaitanya, the floor is yours.
Great. Thank you, Hannes, for the chance to present this this blog post that I wrote together with Rishabh, Anand, my co-author from the National University of Singapore. And the title is Recent Advances in Deep Learning for Routing Problems. And it's really a collection of interesting ideas that this research field has been producing over recent years. And I think today I'll try to make them generally relevant to the graph representation learning community as well. And hopefully, through this talk, I can also give you a kind of map to route this emerging research area. So the agenda for today is that I'll quickly go through some background and motivation, and I'll also quickly go through a unified pipeline to think about some of the research in this area. And I'd like to spend more time talking about some case studies and some recent advances and what that could mean for future work. So this presentation is really not about one paper where I'd be diving into the results. I think it's more about the ideas and more about a myriad of different techniques and how they could be quite relevant. So the main topic is combinatorial optimization, and this is a branch of research that's in the intersection of mathematics and computer science. And the idea is that we're solving certain optimization problems which are specifically NP hard. What that means is that even if you can solve these problems at small scales, it's impossible to solve them optimally at large scales. Essentially, you can't search for exact solutions for these problems on modern computers. And why should we care? Well, these problems are the backbone of many modern industries. And perhaps for this reading group, we should also care because combinatorial problems are usually defined through graphs or sets. And I think we can also preempt many cool recent trends in graph representation learning, as I'll try to show. So one example of a combinatorial optimization problem that is very famous is the traveling salesperson problem. And the idea is that you're given a list of cities and the distances between each pair of cities, and you want to find the shortest possible tour or route that a salesman would take to visit all these cities and come back to where they started. And this GIF is, showing a route through the capitals of US states, and the shortest route is, achieved after some iteration. This is a fairly small example of a TSP, but this problem is notoriously difficult. There's even an XKCD comic on this, and it has some big applications in logistics and scheduling and even in biology and genomics. The comic is funny, but what it tries to tell us is that, if you try to brute force solve this problem, you'd have order of n factorial scaling, which is bad because n is the number of cities that you have or the number of nodes in your graph. Even like standard dynamic programming algorithms are quite intractable for this type of problem. And then they make the joke. So in terms of applications, TSP is part of a broader class of problems called routing problems or vehicle routing problems, where essentially you're traversing a sequence of nodes or cities through some routes among them or some edges among them. And the thing is that your routes must follow some constraints. So for example, for the traveling salesman, you have to find the minimum path or the shortest tour. An example of an application here is that imagine you're Amazon, right? And every few hours you have to send your fleet out to deliver stuff to your customers. And you obviously want to optimize that. You want to save every bit of fuel that you can. You want to do it in the minimum time possible. And so vehicle routing solvers are being run every day, every hour to do these kind of things. And yeah, you can imagine like why I was saying that this is the backbone of certain modern industries. Now, traveling salesman problem is probably the simplest variant of routing problems, but it can get a lot more complex. The constraints can get a lot more complex. So, for example, you could imagine considering multiple salesmen, which are analogous to vehicles in the previous slide, and from there you can consider fixing certain time windows in which you have to visit each city or each node on the graph. Or you could think about adding some kind of capacity to each of your vehicles or your salesmen. So the point is that TSP is probably the simplest problem, and these things can get quite hairy as we move to the real world. Now, how do we solve these routing problems? Or well, we develop certain solvers. I mean, the whole field of combinatorial optimization is caring about developing solvers for these routing problems. And the challenge there is that it takes a lot of expert intuition and a lot of trial and error to come up with a solver for a certain problem. So Concord, for example, is a solver for specifically the TSP. It can't solve other routing problems, but it solves the TSP really well. And in fact, it solves it to optimality for instances up to tens of thousands of cities, but with a really long execution time. And Concord essentially leverages a lot of research in linear programming, but also combining that with cutting plane algorithms and branch and bound algorithms. Now, I mean, what I'm trying to say here is that, for even more complex vehicle routing problems with real world constraints, it's complex to come up with good solvers every time. And that's where we have this big picture idea that can we use deep learning to automate and augment some of this expert intuition, which is required for solving combinatorial optimization problems. And there's a very nice survey from Mila on this broader topic. But what we're talking about today is, one way to hybridize machine learning and combinatorial optimization, and that is neural combinatorial optimization. So the idea is that you want to design deep neural networks as a hammer to hit combinatorial optimization problems as nails. And usually this is at the expense of certain theoretical guarantees, but today I want to kind of motivate why this could be something exciting. So neural combinatorial optimization is essentially using neural networks, specifically graph neural networks, which are at the core of these models, to take combinatorial optimization problem instances and directly try to learn the problem in an end-to-end way, or directly learn to produce approximate solutions in an end-to-end way. And you might ask why, why end-to-end? Well, the motivations are firstly that you don't need to handcraft heuristics for every new problem. Secondly, you can make some really fast inference on GPUs with neural networks, and that can lead to big advances in terms of the real-time kind of problems that you need to make tons of decisions for. And number three, which I find quite interesting and profound, is that you can also now tackle some understudied NP-hard problems, potentially coming from science or computer architecture. And two brilliant examples are, protein folding is usually considered an NP-hard problem. And we all know that AlphaFold has shaken the world with the with so-called solving protein folding. Secondly, computer architecture. So, for example, Google is designing the next TPU pod based on a neural network. So, a neural network is designing the chips that will be used to train neural networks at Google. And I think those are two really cool applications of deep learning for these NP-hard problems.
Oh, yeah, but we're not using any graph algorithms there, right? In the chip design example.
Well, it's in my last slide, but you know that at its core is GraphSage.
Okay, yeah, I didn't know that. I thought, so do they have some reinforcement learning stuff on top of the graph embeddings? I just thought the thing, I just remember that they did something with reinforcement learning too.
Yeah. I mean that's the idea. Combining RL with graphs is the big idea actually.
Okay.
But we can discuss that paper actually. Like I'll come to this stuff in the end as well.
Well, I mean, in the title it says a graph placement methodology, so might be fair to assume that it will have to do something with graphs.
Yes, true. Yeah, I mean, actually, the interesting thing about this Nature paper was that the same set of authors had like a string of related papers. Like you could trace the origin of like this breakthrough through this whole neural combinatorial optimization path in some sense.
Yeah.
I don't know if that's the official version, but like me, as I was tracking the field, I often felt like, wow, like some of the work preempted what they did with the Nature paper. And yeah, I'll be talking about that work, in fact.
All right.
So, yeah, and this whole line of work started with a paper by Oriol Vinyals at Google called Pointer Networks. It was at NeurIPS, and I think that led to a lot of like future work in deep neural networks and combinatorial optimization. So let me go to the next part, which is a pipeline for, I motivated that this stuff is cool, but let me talk to you about how this stuff is done. And, this is where we go into graphs and GNNs and RL stuff. So here's a unified pipeline for neural combinatorial optimization. It was introduced in a paper I recently published last year. And essentially, the pipeline is supposed to give us a map for, understanding some of the advances in the field. Or the pipeline is supposed to unify a lot of recent work in the field in order for us to analyze things. Now, it has 5 stages. I'll go through each one in more detail, but generally, a general blueprint for solving combinatorial problems, and I'm using TSP as an example here. A general blueprint is that you start with a graph, which you feed into your graph neural network to get some latent structural representations. And then you use those latent representations to come up with a probabilistic prediction about your combinatorial problem. And then what you need to do is you need to go from the probabilistic prediction to a discrete solution. And that's where a lot of classical or symbolic search components are mixed with your GNN. And then this whole model is then trained either via supervised learning or via reinforcement learning. And we'll dive into each of the sections of this pipeline just to understand how people have gone about this. So the first one is just to define your combinatorial problem with a graph. And this is usually fairly straightforward. As I said, most combinatorial problems are defined via graphs. And in the case of TSP, it's usually defined via a fully connected graph of nodes or cities. And then generally, people have sparsified the graph based on something like k-nearest neighbors or radius ball queries, especially in order to learn on large graphs or to learn faster by reducing some of the complexity by using sparse graphs. So this part is fairly straightforward for most problems. The second step, and this is where a lot of cool things happen, is that you take your graph and then you form some embeddings for it. So you perform message passing. You stack a certain number of layers of GNN, and you get updated node embeddings for each of your nodes in the graph. And essentially, each of your nodes in the graph now have certain structural features associated with them, which are representing local neighborhood. But I'm assuming that most people here are already very familiar with GNNs. But I think something worth pointing out here is that people in combinatorial optimization had been had made this connection between GNNs and transformers as far back as 2018. It was like something super trivial to them, like they were just writing like, they would just write that in the paper. And I think today we're seeing this connection of GNNs and transformers really being pushed by the graph representation learning community, right? But I think some of the seeds of this idea were being sown in the combinatorial optimization community as well, and they probably thought it was trivial that they were doing this. But I think generally the connection between message passing and transformers, that was one of the places where it was first made. And I mean, I've written a very general equation here, but usually what most papers are following is some kind of attentional GNN here. It seems to work really well for these type of problems in particular. Now,
can we wait a second? So how's your graph usually defined? Either by some distances that you know previously, right? Like if we have some cities, we may look at, or let's maybe not say cities, we can just take some Euclidean distance and take the k-nearest neighbor graph, for example. Or it is the road network, or it is a complete graph if we have no other prior vector. Okay. And then just do some nodes, some message passing, get our embeddings, and then comes the special part of how we use that for the node embeddings, how we use them for our optimization problem.
Right.
All right. Then Surya has a question, I suppose.
So I just had a simple question over here. So in case, I don't know the size of your graphs, but if you're considering a supervised learning setting, is it a challenge to get ground truths when you are having a large graph, or like, is scalability an issue in that case? So in that case, you will essentially have a algorithm solver to provide the ground labels and then train the network, right?
Yeah, we are jumping ahead, but this is in the slides very soon.
I see. Okay. All right. Sorry for interrupting. That's okay.
No, you can interrupt again when I get to that slide, and then
okay. Thank you so much. Thanks. Okay.
Yeah, I think Dominique also has a question.
Yeah. So can you always represent this kind of combinatorial optimization problems in form of fake graph? Like in which cases the graph representation works well for representing combinatorial optimization, and in which cases it doesn't work well.
Right. So I think specifically for the case of these routing type problems, I think it's fair to say that you can always represent them as graphs. Like generally these routing problems are in fact defined in, defined for certain cities, right? So these are usually even embedded in Euclidean coordinates. But I think if you go beyond that, then different classes of combinatorial problems might have different representations. A popular one often is also a bipartite graph. So, if you're familiar with the knapsack problem, then like if you've ever done leet code, then you would be. And this one is often represented as a bipartite graph. And there are also other very classical graph problems like max cut, min flow, which are graphs. Then another super fascinating thing, I think I'm going on a tangent, but there's one problem called the SAT problem, the satisfiability problem, which does represent things as graphs. And a big idea in combinatorial optimization is that every combinatorial problem can be seen as a SAT problem. So if that is true, then I think you can represent most things as graphs. It may not be the most efficient representation, but I believe it should be possible.
And here is the goal to learn a general way of solving like any problems. Like you learn optimization, you learn how to solve combinatorial problems on the TSP problem, and then you transfer on another problem, or like for each kind of problem you need to relearn a new you need to retrain a new GNN.
Great, you've preempted like one of the future cool things that could happen. So today people are mostly like thinking about one type of routing problem and training for one problem, but I think that transferring from simpler to harder problems could be something very cool, right? There must be some shared structure among them, and we could potentially leverage that.
Yeah, that would be great. Like I think it's going to be very hard, but like just imagine a general GNN that can solve almost any kind of NP hard problem. That would be
I hate to use the F word, but do you mean a foundation model?
Some kind of foundation model.
I think that's generally a cool idea. I mean, in fact, like my co-author Rishabh also had this idea, and we were writing about this a bit in the blog post. So like it's in the slides later as well. But I think that is generally a very interesting idea. Like routing problems are having something common, right? So there must be something that can be exploited there.
I had a quick question.
Yes, please go ahead.
So you mentioned about solving the TSP. Is it a function of the sparsity pattern or the structure of the graph, the timing it takes for you to converge on a solution?
You mean for those solvers, like optimization based solvers, or for these deep learning models?
The deep learning models.
Right. So the class of deep learning models that I'm mostly presenting today, for them, once you train it, the complexity of the problem doesn't really dictate how long it'll take them to converge. Like they're kind of one shot, in the same way as, if you feed an image into a convnet, it spits out the answer, right? So the only thing for these models that increases the time is probably the size of the graph that you feed in. But but not the complexity. And that's actually a good point for these models for real-time problems, you know, where if you want solutions really fast, then you can just throw them into this model and it will give you something reasonable many times. Or at least like that's what we think could be impactful in real world. But we also will discuss this stuff later.
Sorry, Kaushku, I muted you because your microphone had some problems. Maybe you can try again later. All right, yeah, shall we just continue?
Yeah, let's continue. Great. I really want to jump ahead to the discussion stuff already, but anyway, so I mean, so once we have those node embeddings, right, which represent some local structure, we want to go from hidden representations in a neural network to something discrete, right? And between that also something probabilistic. So we usually want to, you know, go from the node representations to a probabilistic prediction, which we can train. Like we need probabilities in order to train neural networks, and then to convert that into something discrete. So generally, you know, you'll assign probabilities to either each node or each edge as belonging or not to the solution set. And once you have those probabilities, you will then pass them through a classical graph traversal algorithm to come up with a discrete solution. For training, you just use the probabilities, and to get the final answer, you obviously take the discrete solution. And you know, this is the stage where learning and symbolic AI kind of hybridize. And now the first question obviously is, how do we go from the node embeddings to the probabilistic prediction? I think that is where a lot of architectural innovation also happens. So the first approach and the simplest thing you can do, for example, in the case of TSP, is that you can use a multi-layer perceptron to essentially do link prediction over all the edges in your graph. So your MLP makes a prediction per edge. You know, you take the node embeddings and you try to come up with a value between 0 and 1. And this gives you a kind of heat map of probabilities over your edges in your graph. And then you can kind of feed this into a graph search algorithm, which is, you know, usually you can do greedy search, for example, you know, where you randomly start somewhere and then you pick the highest probability edge, you go to the next node, then you pick the highest probability edge there and you go to the next node, and so on. Or you could do something that we do in natural language processing, which is beam search. So beam search is like, you know, it's a bit like greedy search, but you're essentially maintaining multiple solutions. Like technically it's called limited width breadth first search. So you do BFS, but with a limited width of like potential candidates. But essentially you arrive at this heat map by doing something really simple, by you know, doing link prediction over your node embeddings in the graph. And this can work decently well for these routing problems, as we will see. Now, another approach is to do something called autoregressive decoding. And here you come up with probabilities, or you come up with discrete solutions step by step through graph traversal. So previously we were first coming up with all the probabilities and then using search. But in the autoregressive setup, you actually first make a prediction in each step, and then you take a step of search, and then you follow that and you decode step by step. So in some sense, you're traversing and predicting at the same time, and you're looping through that. And you come up with, you know, a tour eventually. as you follow it. So again, you can do a greedy selection at each step of decoding, or you could do beam search as well. Specifically how they come up with these probabilities at each step, so for example, if I'm here at this node and I need to figure out, well, which node should I go to next? You can compute an attention mechanism among your current node and all the other nodes. And the attention is just trying to compute how important is one neighbor or the other. And you may choose, the neighbor which has the highest probability to decode. And this is called a pointing mechanism in the literature, because it's not really attention, like you're pointing from one node to the other, but the mechanism is attention underlying this. Now, I mean, this comes with certain trade-offs. Essentially, the autoregressive decoders are casting TSP or routing as a sequence to sequence or language translation type task from a set of unordered cities or a graph of cities to an ordered tour. So, you have this tour which obeys a certain order. And this is, modeling the sequential nature or inductive bias of routing. On the other hand, if you go back to this non-autoregressive heat map type approach, right? This approach is going to be significantly faster because, you're not going step by step, but it might be ignoring the sequential nature of your problems. So it can often be about which inductive bias you want to encode or how computationally efficient you want to be as well. And people are, exploring both approaches.
Okay.
See, there's a question,
yeah. Let me first, if you go to the next slide, let me first be a little bit confused about your drawing. So here, this node has 3 neighbors actually, right? So
right.
you really would only be considering the probabilities of going to these nodes.
Right. Yeah, I mean, you're right. I mean,
so
it could be, like, since we aren't dealing with the full graph.
Okay.
Yeah.
Good. But then also, how do you choose your starting node, or will we talk about that later?
We will talk about that later. Right. It's actually really an interesting design decision, but generally, like, people would just choose it randomly, but then folks found out that that's not a good decision.
Okay.
Because there's certain symmetries in this problem.
And for the previous, if you go to the previous slide, how do we go from a heat map to the final TSP?
Right.
Do you just basically choose do something like compute? No, yeah. Will it come later, or how do you do?
No, so in this case, you again do something similar. You start anywhere randomly, like you pick any node to start, and then you run a search algorithm where you're essentially, for example, you can do greedy search. So you can just choose to go down the path that has the highest probability. So you start here, you end up here. Then you again take the greedy decision, so you go down this path and so on.
Makes sense.
But essentially the decoupling here is that the probabilistic heat map is arrived at and then you do search. Whereas in autoregressive decoding, you're computing the probabilities and searching simultaneously.
Yeah.
So there's more coupling between your search and your neural networks predictions, essentially.
So to me, it sounds like the autoregressive decoding should work better. Is this mostly the case?
I don't know. So I think so this is one of the kind of seminal papers in the field by Wouter Kuhl and others from the University of Amsterdam, and they this paper really pushed for the autoregressive approach. And it worked really well. But when I was writing my thesis with Xavier Bresson at NTU, we had this paper where we tried to push the non-autoregressive approach, and we were able to outperform this method. And I think that led to 2 lines of architecture. So people are really innovating on autoregressive models, but I'll show also later that people are also innovating on non-autoregressive models. And
yeah,
I think they're really like head to head in some way. Like I don't know if one is better or the other.
okay. Well, Guahao is bringing up the interesting question, like that the edge decisions are not independent of each other. Like in the autoregressive decoding, for example, we, yeah, but I think you'll get into some symmetries that we could consider there and want to consider there at a later point. Yes, no?
Okay. I'm trying to read the question.
Yeah, I just mean we can maybe move on until you bring up the symmetries of, for example, choosing.
Yeah, I think it'll be relevant there. Yeah, I think we will, come back to this there.
Okay.
So the last part of this whole pipeline is that, your graph embedding, your decoding, and potentially your search are all learnable, right? So how do you train this end to end? And the simplest thing that you can do, as one of the questions also alluded to earlier, was that you can imitate an optimal solver. So you can do supervised learning. And we talked about Concord, which we can now use to generate a huge labeled set of TSP samples, for example. Or, if you're dealing with another problem, you can use another optimal solver, as long as you have an optimal solver. And then depending on the decoding that you use, for example, you can just train that via supervision. So autoregressive models, as I said, were really mimicking seek-to-seek from NLP, and the way to train them is exactly the same through something called teacher forcing, where you're outputting the optimal sequence of nodes. Then the edge approach, the non-autoregressive heat maps, you can train these heat maps to simply make a binary classification over edges which belong or don't belong to the optimal tour. And this stuff works well as long as you have a solver. But obviously, this is far from ideal, because like when you start scaling to large or real world graphs, supervised learning is going to be extremely expensive and time consuming to even generate the data set for, especially for large problems where the guarantees of optimality are not even always true for solvers. And there's some interesting theoretical work which actually says that if you use supervised learning to solve these NP-hard problems, you may actually be solving a simpler sub-problem that you can generate data for. You may not be solving the actual NP-hard problem. And I will talk about how that impacts practical things later as well. But generally, supervised learning is the simplest thing that we can do. But something very interesting or elegant is that routing problems, or generally combinatorial problems, are optimizing a cost, right? They're minimizing a certain cost. So for TSP, it's the tour. And this can very elegantly be cast into the reinforcement learning framework. So especially for these autoregressive decoders, you're doing some kind of sequential decision making. You're learning to make sequential decisions, and you can now train this via either standard policy gradient algorithms, which usually work well, or via deep Q learning. This is a wrong citation. I should change that. So deep Q learning was from the paper by Elias Khalil, Hayun Dai, and others at NeurIPS. But essentially, you can cast these problems as RL because you're minimizing a cost function. And this is really great for those problems where you don't have ground truth solvers or ground truth solutions. For example, chip design, as we'll discuss later as well. So reinforcement learning can essentially allow you to do certain decision making on your graphs without, as long as you have a cost that you can minimize. And that's the pipeline. That's the like 5 stages of this pipeline. And, you know, we can characterize prominent papers via the pipeline. So we can kind of look back and, you know, say like what were the big ideas with each of the papers, and we can break them down into these 5 stages of the pipeline. And, you know, in red, I've highlighted the big ideas. So as I was saying, that Vinyals and others' paper basically introduced like this whole idea of doing sequence to sequence with a pointer attention decoding to solve combinatorial problems. Bello et al., which is also from Google Brain, basically took the pointer network model and trained it with RL instead. And that led to improved performance and also, you know, the subsequent lines of work on chip design as well, I believe. Khalil's paper was the first one to have the graph perspective. So they introduced sparse graphs to represent these routing problems and other combinatorial problems. And at the time, you know, one of the first GNNs called structure to vec. I think today maybe like others are more popular, but structure to vec was one of the first GNN models from Georgia Tech. Was used, you know, at the core of this model, and it was also trained via deep Q learning. So we can essentially use this pipeline to, you know, think about what were the innovations happening in the field. We can do more as well. So for example, the paper by Kuhl and also the paper by Deodon subsequently introduced this idea of using transformers to encode graphs or fully connected graphs. And then this work that I did was introducing this whole heat maps idea of, you know, thinking about these edge probabilities and then applying some search on top of them. And essentially the pipeline gives us a mental map of this research field. And we can then use it to think about exciting new ideas next, which is the fun part. But before that, a short note on performance, right? Like as a bridge to the fun part.
Before that, a question.
Yeah.
How do you come up with these losses for chip design, for example, or the reward functions in reinforcement learning,
right?
Objectives, right? We have the question, isn't it very hard if the reward only comes at the end? Because only at the very end we know how far we are from how big our distance is on the graph.
Great point. So like maybe I should have mentioned that as one of the plus points of supervised learning, right? Like you have more signal with supervised learning, but with RL, it's a really sparse learning signal, right? You only get a reward at the end. So that is what makes RL tricky, and that is what in fact makes this, you know, makes it challenging for RL to scale to large graphs. I also think it's a great bridge into the performance part. That, you know, like just this challenge of scaling to large graphs. With reinforcement learning, the challenge is that the reward is really sparse. With supervised learning, the challenge is that you can't generate samples for large graphs. And this is what we've seen in the field, you know, like in all the papers that I introduced so far, essentially, like we only looked at really small TSPs, like up to 100 cities, but this is pretty far from what we need practically. So what we've seen with each paper is that we're always improving the average tour length. So lower is better in this case. We want shorter tours on average for 50 or 100 cities for some random samples. And what we saw with the first string of papers was that we were already kind of below 1% of closeness to optimality, where Concord was, a way to define optimality. So a very experimental way to evaluate these methods, but we were already really close to 1% for solving TSPs with 100 nodes. But so as the bridge to the case studies and recent advances, the big challenge is, how do we scale to large TSPs, and how do we scale to real world TSPs, or how do we scale to real world routing problems? And as I said, learning from very large graphs is a challenge for RL because of sparse reward, and for supervised learning because you just can't generate data. And essentially, the solution is to generalize, or to build models that can transfer from small or synthetic instances of combinatorial problems to larger and real world instances. Now, obviously, this transfer will not be perfect, but it seems like, it seems like if you can't directly learn on the large instances, then you at least need something useful there. And I think in the next sections, we'll just discuss some cool ideas from the research community. None of it is my own work, but cool ideas from the community to try to do this. And I think there'll be also some interesting consequences for GRL in general. Yeah, I see there's a question.
Yeah, I just want to know if right now there's any work that observes this kind of generalization from small to large scale, or is it, yes? Okay.
Yeah.
Is it in the next slides, or?
Yeah, it's in the next slide. In fact, we'll discuss all those works. So for me, in my research, I'd kind of tried to do this, but maybe not been successful. But essentially, this blog post was a way to cover all those papers which have been successful, and it has a lot of cool ideas. So the first big new idea in this field, or recent idea in this field, is leveraging equivariances and symmetries. So we talked about this at the very start. In general, if you think about the autoregressive decoding techniques, right? You're casting a sequence to sequence, and your solution is a permutation of cities. But this ignores a certain symmetry about routing, in the sense that, if you have this route on the left, then in the sequence to sequence decoding format, you could start at any of these nodes, and that would mean that you have a different permutation of routes. So essentially, you're making it really hard for your model if your model has to now learn that all these permutations are actually the same route. And one solution to this one was called FOMO by Quan et al. At NeurIPS 2020. They were basically leveraging invariance to the starting city in routing. They essentially took Kuhl et al.'s model, but they devised a new RL objective or way of doing rollouts in policy gradients, such that the model was aware that you can basically, the model would be aware that all these permutations are for the same tour. But this idea can be pushed further. Equivariances and symmetries are a really powerful idea, right? So another upgrade on Kuhl et al.'s model.
Can I interrupt again? How does this work?
How does this work, right?
Yeah.
So in reinforcement learning, when you're doing policy gradient, you're usually computing rollouts for your model. You always want to penalize your model for being worse than it previously was, and reward it for being better than it previously was. And the way that the way that they enforce this invariance is that, generally during the rollout, they might, I don't think they start with all the cities, but they have some kind of stochastic or random way of starting from multiple cities and computing multiple rollouts during the RL loss function calculation. And that allows them to, significantly boost the performance of this model.
Like, I see the point that if we were to start from every city and then just average the rewards from all the different starting points, then I see how this would give us the invariance. But if you don't say that we start from every city, I don't yet see how it works, but I suppose for the curious like me, we'll have to have a look at the paper.
Yeah, I think so too, because it's not on like super on my fingertips right now as well. I think I also don't know exactly whether the invariance is, provably invariant or a kind of, approximate invariance.
All right, then I will. Oh no, Surya's question came back up.
Yeah, I just had a question from, I think, the previous slide where there was a question regarding the scalability in reinforcement learning settings.
Right.
I think recently there was a talk by Elias B. Khalil in the Mila group in which he explained online bipartite matching problems.
Right.
So, and again, so regarding that case, I think there was an interesting point where we could see just one node at a time and, employ policy gradient methods to actually learn things. So I was wondering, is it even possible to extend that kind of concept in TSP settings? So I don't know whether it's fully relevant in this case.
Unfortunately, I wasn't able to attend the Mila reading group. I wanted to, I wasn't.
Okay, maybe we can take it offline. It's just like regarding scalability and how the RL constraints can be posed better. I think maybe we can just talk about it offline.
Yeah, I'm sure there are super interesting ideas there as well. And I mean, a lot of times the ideas are, transferable from one type of combinatorial problem to another. So maybe nobody's done it for routing yet, but it might be highly relevant.
No, I was just trying to I don't know whether it can be done in reality at all. It was just posing the question to understand whether you already know the paper and maybe if that can be extended to this kind of problems.
No, unfortunately, I don't know the specific.
That's absolutely fine. Yeah. It's okay. Thank you so much.
Okay. Yeah, so the idea of equivariances and symmetries is really strong, and you can do more with it, right? So these routing problems, if you look at a solution here, or if you look at these set of coordinates or cities, they're usually embedded in Euclidean coordinates, or I mean, they're always embedded in Euclidean coordinates. Like you're routing in the real world essentially. So it shouldn't matter how you rotate or reflect or even translate this set of coordinates. It shouldn't matter to the final solution, so the final solution kind of rotates or reflects along with the coordinates here. And essentially this paper called eMagic, it's a long acronym, which I wouldn't say, but this paper upgrades the attention model by Kuhl et al. with equivariance to the Euclidean symmetry group for the input cities. Now, they ensure equivariance by doing data augmentation to increase the size of their training data set. And they also use relative coordinates or distances only during graph encoding. By my understanding of equivariance, like the second part may have been enough, but or like the second part may have just given them an invariant model, but they call it an equivariant model, and they also have data augmentation where they are rotating, reflecting, and translating coordinates during training. And what they show is that they get some really strong results when they train on some random TSP instances and generalize to real world instances from TSP-lib, which is a benchmark of these TSPs in cities like Berlin or Paris, or like other cities around the world. Like essentially these are real maps and you're trying to do routing in them. So this was a very recent paper, which was adding equivariance or this like lens of symmetries into the mix. And the big picture here is geometric deep learning, right? Like this is a big idea in deep learning these days, and it's telling us to explicitly think about and incorporate the symmetries and inductive biases that govern data. And for routing this, some of the symmetries are that these are embedded in Euclidean coordinates and that the routes are cyclical. So if we can try to break this stuff down again using the pipeline, what we can see is that you can start with the model of Kuhl et al. And you can add a new type of rollout to it, which helps you be invariant to the cyclic or to incorporate the cyclic nature of routes. Or you can use an equivariant graph neural network or an invariant graph neural network to process these coordinates or these cities, and that can help you incorporate the symmetry to the Euclidean group as well.
Wait, so where they do the invariance, that's not actually the paper by Kuhl et al. Like with the starting node invariance, that's the paper by Kwon.
Yeah.
Oh.
Yeah.
Oh, okay.
Yeah. So what I'm trying to show with this table is that you can try to characterize like where this paper is over Kuhl et al, right? And essentially all else is the same except this box.
Yeah. I was now looking through the Kuhl et al paper for a few minutes, trying to find where they solve this invariance. But
no, sorry, it was Kwon et al from Neurips. The link is in the blog post. The next, so beyond geometric deep learning, there's also another big idea, which is the search algorithm. So it seems like somebody's laser pointers on, but so when we think about these GNN models, right, they're usually giving us a prediction, and then we have to use search to traverse this heat map. And specifically, these are those non-autoregressive kind of models. These are these non-autoregressive kind of models which are giving us a heat map, and then we can have a search algorithm. So what people are doing is to really try to push the search algorithm here. So beam search or greedy search is probably the simplest thing that you can do. But recently there have been works trying to apply dynamic programming as well as Monte Carlo tree search to the same framework. You just swap out the search component with something more powerful, something more flexible. And this seems to actually significantly help you generalize to larger graphs. And a great example of this is this work of Fu et al. At AAAI, which was basically using Monte Carlo tree search, but with a very special approach. And the approach essentially was that, when you deal with huge or large scale TSPs, you can think of them instead of as a single graph over which you have to, encode your nodes with a GNN, you can think of them as a set of smaller subgraphs. And they very cleverly set the size of the subgraphs as the same as the size of the TSPs they use for training. And then during the search component, they essentially stitch the predictions from a GNN together and then search over that. Essentially, they divide and conquer. They take a large graph, they sample it into smaller sizes. So this could be 1,000 nodes, and then you have subgraphs of 100 nodes each, which you then pass through a GNN. You've trained the GNN on 100 node graphs, and you get a heat map out of it. And then what you do is you merge the heat map and then perform search. So you perform search after merging. Whereas if you just run your GNN directly on the full graph, your GNN would just not be able to generalize if it's never seen large graphs. So for example, they even tackle graphs up to 10,000 nodes at 3% of optimality, which is, I think, really strong through this approach. So they train on very small graphs, like even up to 100, and they're able to go up to 10,000 through this kind of divide and conquer style approach. And if you know where this picture is from, I think you can also like start making this cool connection to what is happening today. Like what is a big idea generally graph representation learning is, these subgraph based GNNs, which are trying to also treat graphs as a set of subgraphs and thinking about how that could, potentially lead to more expressive power or help the model perform better. And I think there's a neat connection to, what was happening in the combinatorial optimization world as well over here. Now, and so what does this actually say, right? Better search and divide and conquer type strategies suggest that you need a stronger coupling between the design of the neural component, so the graph neural network and the decoding, combined with the symbolic or search component. And I think these two works really were showing that you can generalize out of distribution really well if you set up your search in a very smart way. Like you can get a lot of mileage out of searching in a smart way. And again, I've tried to use the table to show, what are the new ideas that these works were bringing in, mostly like in terms of adding new search techniques into the mix. And in particular for this work, also thinking about, graphs as a set of subgraphs. Yeah. Is there a question?
Yeah, I just want to say, like, from the previous slide, when you said that it generalizes well if you take many subgraphs and you run the TSP on all these subgraphs and you combine them together. But when they tested on the full graph, it didn't work well, right?
Like if you imagine this as a graph with 10,000 nodes, if you've only trained your GNN on 100 node graphs, then it'll never generalize, or it'll never generate something sensible for a 10,000 node graph.
But did they try that, or not really?
I think so. So this work, for example, is building upon the previous heat map approach, right? And I remember personally trying that and completely, like it completely falls apart. Like I think generally it's graph neural networks sometimes are struggling to extrapolate to graphs more complex than what they've seen in training, right? Or even sometimes larger than what they've seen in training. And this divide and conquer or subgraph approach was a way to just mitigate that problem, by dividing it into problems that that the GNN can solve, or you've trained the GNN to solve, and then having this special way of stitching it together, and then performing the search on it.
It would be nice here to see, like, for example, if you trained on 100 nodes, and here you test on 10,000 nodes, when you can easily see that 10,000 is 100 times 100. So it would be nice to see, like, if you cluster, if you pull your graph into another graph of like 100, another graph of 100 nodes, learn a TSP on that graph, and then on each of the subgraph, like learn again the TSP, but then make a connection between what you've learned into the pulled graph and what you've learned into the subgraph, instead of just like combining subgraphs naively like that. I think that could be a very nice approach to scaling to larger graphs.
Yeah, I think you have a really strong intuition for this. Like, I believe some people might actually be working on that. But yeah, I think like that hierarchical processing could be really interesting, right? To scale through this kind of method. Like, you're right, like randomly sampled subgraphs are not imposing hierarchy, but maybe adding hierarchy could be a sensible idea.
Yeah, so in some sense, if you take the full map of a given country and want to learn to execute the TSP on that,
right?
But you've only learned the TSP on a single city, well, you can just view the pooled version as learn which city to go first, which order to do the cities, and then learn in which order to do the deliveries or the sales that you want to do in each of these cities. Because otherwise, like if you don't do that pooling approach, in some sense, you can go to one city and come back to the same city later at a later point. So it would kind of have also a good inductive bias there. And as you said, there's probably some people working on that.
Yeah, no, I think it's generally a good idea. Like it seems like something that should work, right? Yeah.
Surja, now, let's go ahead.
I think they just haven't unraised their hand.
Yeah, sorry. Then let's keep on going, and I'll unraise the hands.
Right. So another interesting approach is, it's coming really as an alternative to the previous approaches, where previously we were really constructing towards, or we were learning to construct. Another approach is learning to iteratively improve solutions. This is actually how most classical solvers are designed. They're designed to iteratively improve certain solutions, and they also come up with some theoretical guarantees based on that. Another way to look at it is that you're learning to perform local search. So what you can see here is that, in this GIF, you're making small local changes to a solution. And if that improves, then you make it your optimal solution. And if it doesn't, then you keep making more local updates. So these local updates were previously done based on heuristics, but the big idea with these works is that you can now learn to perform these local updates. And essentially, you're still guiding the decisions within a classical search algorithm or a search heuristic. And these heuristics or algorithms are going to work regardless of the scale or complexity of the problem. Like, if you give them enough time, then they will come up with a reasonably good solution. So learning to search may, implicitly give you better generalization to larger graphs. And I think this is like a really interesting idea that way, that you can put learning inside some classical solvers. So two works in particular which were really interesting and presented at this year's NeurIPS. One was combining learning to search with symmetry. So it was called dual aspect transformer, and essentially they were using a transformer or GNN to update both the structural and positional encodings. And they also came up with this notion of cyclical positional encoding. So they said that, for these combinatorial problems or these routing problems, if you care about the position of nodes in your route, you can't just use or borrow the ideas from NLP. You need to be very careful about how you encode position. So they came up with a smart way to essentially come up with positional codings which respect the cyclical nature of these tours. Another example is a neuralized version of this heuristic called Lin-Kerrigan heuristic, LKH. So besides Concord, LKH is probably the most popular and successful heuristic for solving large TSPs. And this one's results were super impressive as well, that they were able to solve up to like 5,000 node TSPs with less than 1% optimality. Although it can take a bit of time because, as I said, like they're iteratively solving. Now, for this line of work, I mean, the architectures are kind of similar. Like they're creating a new paradigm, right? Like they're learning to do local search. So they do a lot of interesting things in terms of how they design the decoding and the search algorithms. So generally, like we're seeing decoders that are highly specialized to these routing style problems. As I said, like you can't directly import ideas from NLP very successfully. And I think these approaches are also pointing to another like interesting connection in graph representation learning with neural algorithmic reasoning, which is giving you a kind of meta way of thinking about hybridizing learning into some classical algorithms. So these local search algorithms are in my mind like analogous to something that neural algorithmic reasoning is also doing, but potentially for NP-hard problems as opposed to the like graph algorithms that it's mostly tackling so far. I think I'll jump ahead from these. Like there's also some learning paradigms that are specifically trying to promote generalization, and the one of them is what Dominique was talking about. Like, can we do pre-training, and that might allow us to transfer to new routing problems. There's also calls from the community to really get real about this stuff. Like go from the lab to the real world, and there's both like theoretical issues and practical issues with this. So in theory, like what I was talking about is when you evaluate these algorithms, you generate data. When you train these algorithms, you generate data about an NP-hard problem. But there's work showing that whenever you generate, you might be generating data for a simpler subproblem as opposed to the real NP-hard problem. So like the title of this paper is really interesting. It says, it's not what machines can learn, it's what we cannot teach. So their thesis is that you cannot actually teach a model to solve NP-hard problems. So then when we think about practice, then there's similarly been complaints from the OR community that the evaluation protocols are not very sensible, and there's also been like a new set of guidelines to try to make this stuff really practical, including some competitions at top conferences as well. But I think the more interesting thing, and I want to quickly finish, is the more profound motivation of doing this stuff, right? Like routing problems and optimizing vehicle routing is really practical. Like there's a lot of like savings and money there. But another like profound motivation that this original paper from Google Brain was talking about is that this can be a general tool for tackling some previously unencountered or understudied NP-hard problems. especially those which are non-trivial for humans to design heuristics for. So to give you some cool examples that I really like, the first one we already talked about. This is the big one in nature. This is from Google Brain. Like, they're essentially designing TPUs with this neural combinatorial optimization type framework. And how they set it up is, you basically have an RL agent that is learning to place certain things in a chip one step at a time. So autoregressive decoding in some sense. But the state space or like how they encode the problem is via a graph. So they have certain features and it goes into a graph convolution. And then they use the embeddings produced by that to pass it into a convnet decoder, in fact. So the decoder is coming up with, this type of grid prediction. And then they train it using RL to minimize certain metrics about computer chips. So generally they're using metrics like the negative of the wire length, like how many wires the chip is going to have, and congestion or density. So these are metrics that you can compute very quickly. Like, you can compute them in simulation, essentially. Like, you don't need to build the chip to compute them. And this like GNN plus decoding plus RL framework is essentially powering this kind of model. Some other ones which I found really cool. One is on communication network optimization. So like our internet networks or wide area networks, right? Essentially here you have these networks and sometimes some bottleneck or traffic forms on them, and then the question is, like how do you I guess cut or open certain paths to mitigate that traffic? And here again, like, the networks are graphs, so you encode them via GNNs, and then they cleverly set up a reinforcement learning combined with local search. And again, like, they're able to define some of these metrics that they want to minimize with RL in a kind of synthetic way. Like they don't need to realize the whole thing. I guess they use certain metrics to define like traffic or crowdedness. So this is for communication networks. Something super cool that is from genomics. So in this case, like, so there's this problem in genomics called genome sequence assembly, and essentially the problem is that you can read genomes, but you can only read them in fragments, or in this case nodes, and then you need to find a path through these nodes. You need to thread the needle through these like soup of nodes, and it's a problem that has a huge impact. I mean, like, understanding the human genome or genomes of other organisms, and this problem can be cast as finding a path through a graph or finding a TSP like tour through the graph. And recently Verchik et al. Applied this graph convnet plus beam search decoding, like heat map type approach to genome sequence reconstruction. And in this case, they were using supervised learning because we have like basically the full human genome at this point. But it could be interesting to now like learn to assemble the genomes of like other organisms, or generally it took like 30 something years to assemble the human genome. So maybe if we have a deep learning model to initialize some of that and do a bit of the heavy lifting, then that could speed up the assembly of genomes of other organisms. So I guess what I'm trying to show is that there are all these interesting NP-hard problems out there that we can't maybe precisely define with mathematics, and we can't maybe build great solvers for, but this this approach of neural combinatorial optimization could lead to some really cool advances over there. In fact, I mean, in chip designing, it already is. Like, it blows my mind that the next TPU will be designed by a neural network to train neural networks. I think that's pretty cool. And yeah, thank you very much for attending. Apologies for overshooting, and thank you to my co-author, Rishabh, an undergrad at NUS, and my collaborators on the papers, Xavier Bresson, Thomas Lauren, Quentin Capad, and Louis-Martin Rousseau, for helping me navigate this research field as well. And obviously happy to chat about anything.
All right, perfect. There is no overshooting. We're happy to go for as long as it takes, and we have no 1 hour limit or anything like that. But awesome presentation, and thanks for already answering so many of our questions. Does anyone else have questions?
Yeah, actually, I have a quick question. So I'm curious about how can we evaluate the quality of our solutions on a very large scale graphs. I suppose we have a graph with millions of nodes, right? So typically, like for these NP-hard problems, we cannot know the optimal solutions, right? So,
I think you like arrived at this like really like tough problem, right? Like, how do we even begin to evaluate for super huge graphs? I think we can't, right? Unless we are able to resolve the P versus NP conjecture, right? So I would point you to this reference though. Like, this is a great paper to read about this exact matter that you pointed to.
I see. I will check this paper. Thank you.
But right, what we usually do is that we look at, we try to get as close as possible as to Concord, for example.
Yeah. So even for Concord, right, it's not able to give you optimal solutions beyond, say, tens of thousands of nodes. Like, the largest graph that Concord solved the TSP for is something like 100,000 nodes, and it took a few months to arrive at the optimal.
What you wanted to say is not what you wanted to say is not that it is not able to give you optimal solutions. You wanted to say it's not able to give us approximate solutions, right? Concord also only approximates the solutions of these mid-sized graphs.
Right. The thing with Concord and several of these solvers is that they actually do prove optimality. So in fact, like, Concord can give you a solution for a TSP with millions of nodes. It just will not be able to prove its optimality. Like,
so it is just an approximation, right?
Yeah.
All right, Tom, what's your question?
Well, I'm thinking about that, and I think that there could be some ways of making the network evaluate itself, even if we don't have an exact solution. One way that I'm thinking like is, imagine the network finds a certain solution for the TSP on 1 million node, and you have no idea, like, is this solution good or not? Well, one thing you can try is a set of random permutations. Like, you do a random permutation on the path, and you do that many times, and you look at how much this new random permutation affect the total path that you have, and you can try like different scales of permutation. And I don't know, I think it would be interesting to look at this kind of thing and look at what does the gradient look like around that solution. And for example, try it with 50 nodes, 100 nodes, 1,000 nodes, and look like how does the perturbation affect the optimal solution, and see if there's like you can find a trend between the actual loss and the effect of permutation on the the solution.
Right. Right. Like you'd basically permute the proposed solution of the model and try to see if it's worse, right?
Yeah.
In fact,
try to see by how much it's worse. And
right. Right.
Yeah.
I think that is one of the ideas powering also this whole local search paradigm. So what local search is saying is that I will start from a solution. It could be a bad one or a good one. Then I'll try to make small local changes to it. And there are certain tricks to doing this. So for TSP and routing problems, you have certain operators for local search, but for other problems, you have new operators. But essentially, you have to hand design some of these operators or perturbations. You keep trying them. If they improve your solution, then great, you've improved the solution. So you keep that solution. If they make it worse, then you have a smart way of rejecting this. And essentially, the idea with local search is that if you do it for long enough, you start from something random and you do it for long enough, you will arrive at something good, right? So then with the idea with learning to do local search is that if you can firstly start at something already pretty good, maybe by learning, and then you can learn to do these local search operators, you can significantly accelerate the local search process. But I think I didn't think of it in a way of evaluating models.
Yeah. Well, instead of doing small perturbation, what about doing perturbation all around the path, and try to do bigger and bigger perturbation and look at the gradient of look at the curve of how much perturbation impact the optimal solution, and try to find a trend there. Can you predict what would be the optimal solution from the gradient of the perturbation? And that way you can not predict the optimal solution, but predict the loss to the optimal solution.
Right. Is that what you wanted to refer to with the diffusion-based approach in the chat?
No, for diffusion-based approach, I was just maybe that's how the loss work, but I was just thinking, this is how diffusion-based generative models seem to work. They start from completely random noise and they generate something solid from that. And I think it would be nice to look at how that would work in here, but I guess this is just some.
That would be an idea, right? That we start with an optimal, or we start with our optimal path, or maybe only approximately optimal path. But yeah, let's say we always have optimal paths, and then we add these edges have the node or the edge probability 1, the optimal ones, and the other edges have the edge probability 0 in the beginning. And then we always add a little bit of uniform noise to each edge, and that's our forward process. And then we try to learn the reverse process, and maybe we can end up with with a diffusion model that gives us a heat map that we can then use, like Chaitanya used it in his paper.
Yeah, I think diffusion models could be very efficient for TSP problems, in fact, if you have the solution. Now, if you don't have the solution, the idea is doing the reverse. Adding small noise, adding small noise, adding small noise, how much your solution becomes worse and worse and worse each time you add noise, and try to predict what would have been the optimal solution there. I guess the closer you are to a global minima, that's maybe just a wrong intuition, but my intuition is that the closer you are to a global minima, the more noise will affect your choice. So yeah, but I really think also diffusion model could be impactful here.
Right. The point about diffusion models is particularly interesting because there's a nice parallel between like what we see in molecule generation, right? And some of these routing type or combinatorial problems on graphs. Like essentially generating a graph or generating a molecule could also be thought of as like a search in a combinatorial space of possibilities, right? And I remember recently there was some success of diffusion models, right, from Mila on doing this like molecule generation stuff.
Yeah, but like I still think this is a very different problem, right? And we have some discrete stuff we want to do here with edge probabilities, and like I don't actually think that this sounds promising to try to just take a ground truth solution and then add uniform noise as a forward process, and then end up with completely noised edges in the end, and then try to reverse that process. But it's still super interesting to try. Like,
why does it work well for molecules though? Like
for molecules, I think it is kind of modeling the physics a little bit. And I mean, we can always just add Gaussian noise and just have basically the perfect scenario for where I think diffusion models should work the best. Yeah. But anyway, let's maybe get.
We have. Yeah, no, I just want to say we have to be careful here with diffusion models. Also, if we just decide to add a bit of noise on every edge, the model can just learn to keep the edge with the highest intensity. So there would be a trivial solution here. So we have to be careful, like how can we actually use the diffusion models? But it could be interesting to explore.
I'm not sure what you mean there, but I'm also not sure how exactly we would use a diffusion model to address the or how a diffusion model could well be used to solve a TSP problem. But let's maybe also get to Zorgia's question.
Yeah, I just had a question related to what Dominic asked about injecting noise into the network. So there has been a recent work about solving neural combinatorial problems using adversarial robustness. All right. So where you have spurious features, and exactly that's precisely a concern where it's difficult to get ground truth labels at a large scale. And they get provably optimal solutions. It's, I think, a work from TU Munich groups, and the author also presented in Mila. So I was wondering whether the methods that Dominic discussed, whether it's comparable to adversarial robustness for solving neural combinatorial problems.
Yeah, that's an interesting perspective. So I don't recall exactly how they added the adversarial noise to samples. Maybe.
In the chat group, it's a 2021 paper though.
Right. Yeah. It was just accepted at iClear 2022 now, but yeah, generally they were adding adversarial noise as a way to make the model more robust, right?
Exactly. And they prove that under certain conditions, you get proved the optimal solution.
Oh,
I see.
What paper are we talking about?
Yeah, I'll just share the link. Just a second.
Okay, thanks.
It's a recent paper from TUM by Geisler et al.
Yeah.
From Stefan Gruneman's group. Yeah. But yeah, I mean, it might actually be something similar, right? In terms of how they define the noise.
Yeah. Okay. All right. Thanks for sharing the paper. that was definitely a great introduction into the field of routing problems and solving them with deep learning methods instead of the traditional methods. And if you want to join the reading group sessions yourself, you can find all the information in the description, including the mailing list or the Slack channel, where we will get weekly updates.